Activation functions in neural networks. For this lecture, we need prior knowledge of what a neural network is. So, if you don't know what a neural network is, please DM me in the comments and I'll share the link of my earlier lectures. So, activation function is applied in the hidden layers of the neural network. Neural network, as we know, it has input layers and output layer, and we train the data of the input layer to get our correct output for the output in the output layer. In between, we have hidden layers with hidden neurons. Why we call them hidden? Because they're hidden from the user. The user just inputs the values to the input layer and we see how the output is. The more complex the problem is, the more hidden neurons, hidden layers we can have. Our aim is to classify, to make the computer model which can mimic the human brain, right? So where if, say for example, I have a cat, a set of cat, a dog, and probably a rat. So I want my model to classify them correctly and tell correctly, predict it correctly, which one is the cat, which is a rat, and which is a dog. So for that, I need to train the data. The activation function is very helpful in the hidden layer for the training of the data. It is a mathematical function applied to the input neuron to decide the output for the hidden next layer. So, like I said, for the input layer, I have the given set of values. For the hidden layer, the input was decided on the input neuron and the activation function. So that is the next layer, and more the output for the hidden layer will move forward for the next hidden layer. It transforms the weighted sum of inputs, means we use some weights along with the inputs, which is then passed to the next layer. Also, and times we add a bias function. If we don't use a activation function, what will happen? If we don't use activation function, the input will directly go transform to the output like a simple linear model, and any real world problem cannot be solved with direct linear transformation. For classic problems like we face the image classification or speech recognition, we need the training of the data going through hidden layers, training, retraining, and application of those mathematical formulas to get the correct output. Now, suppose we have uh, a specific problem, which I in my earlier lecture I told can be found classified into two ways: a classification problem or a regression problem, like a supervised learning, unsupervised learning lectures I had said. So, for all that, we use different kinds of activation functions. But anyway, how we have the weighted sum, and we have the bias which calculates the input to the hidden layer neuron. So once we add the bias, our output looks like this. In general terms, the output neuron will look like a function of the hidden neuron multi- and multiplied by the weight which we decide plus the bias added to it. Now, for different kinds of problems, since we have artificial intelligence being used in so many fields, we have different activation functions for different kind of problems. That depends on the user, or that depends on the designer, which problem is will require which kind of activation function, which hidden layer will require which activation function, so that our data is trained little more accurately, right? So we have basically, I can classify the activation function in three ways: linear functions, non-linear functions, and exponential linear functions. Using the right activation function leads to faster training and better results. Linear activation function, as you can see, it gives the linear transformation to the training data set. The main use of the linear activation function is in the output layer of the neural network. Linear activation function is not used in the hidden layers because it is just linearly transforming. It is not squashing the predicted value. The graph shows a hidden line and the graph shows a straight line, and the range is from minus infinity to plus infinity. Nonlinear functions are like several of them, like the tan hyperbolic function, the rectified linear unit, the leaky linear unit, the exponential linear unit, and so many else. As you can see from the graph of the hyperbolic tangent function, the output ranges from minus 1 to plus 1, and that means it results in faster learning and faster training during the training learning period, learning of the hidden neurons. The rectified linear unit again is means if the input is positive, it will return the value, same value. If the input is negative, it will return 0. So this is computationally less expensive, the rectified linear unit. That's why more popular. Computationally less expensive means the processing power is less as compared to other activation functions, the memory, the time used is less. It is always and always used in the hidden layers and never for the output layer. Similarly, for the other nonlinear for activation functions. The sigmoid activation function is an exponential linear function and it is very, very differentiable function. The value, output value lies between minus 1 to 0. Thanks for watching. Do like and subscribe to this.